Hi, this is Benny. I've dedicated my life to understanding the universe in hopes that someday I am given the opportunity to hop on a rocket and see it for myself. Growing up, my safe space was between the covers of a book. My friends were people like Percy Jackson, Alex Rider, Paddington Bear, Beatrice Pryor, Hermione Granger, and the Astrosaurs, a group of crime-fighting dinosaurs in space. And so, using Space Bites, this podcast, I am hoping to create the same type of safe space where knowledge is for everyone and anything is possible. Together, we can marvel at the boundless beauty of the universe and find hope within the delicate intricacies that weave the fabric of our world. If there's one thing we have in common as human beings, it is our curiosity, and a curious mind is a happy one. Together, we will learn how the gold in our rings was made inside of stars, how the flap of butterfly wings can cause an earthquake, how charged particles from the sun interact with Earth's magnetic field to paint the sky with glowing lights, and how math is the language that describes everything. Every atom in your body was created in a star. The carbon in your DNA, the oxygen you breathe, the calcium in your bones, all of it originated in stellar furnaces. This means that quite literally, the universe is in you. You are a product of cosmic alchemy, billions of years in the making. The same processes that formed galaxies also formed you, linking your existence to the vastness of the universe. Hello everyone, and welcome back to another episode of Space Bites with Benny. It's me, Benny, your favorite nerd. Today we're talking about galaxies, what they are and how we study them, and we have a special guest, Alex Potter.
Hello, everyone. It's nice to meet you all. Yeah, I'm Alex. So, Banana and I met in Durham last year, as we're both avid physicists, and we met during our labs. Yeah, and we found very quickly that we connected quite well. We were equally driven, equally interested. And yeah, it was a very natural friendship.
And just to give a little introduction to how our friendship was solidified, and until now it's still one of my favorite days. It was like one dreary November evening. I was super sick. I had a fever and I was at home when Alex calls me up and he tells me that there was an an aurora sighting in Durham, and he says, "Where are you? We're in the physics building, and we're waiting to see the aurora. You have to get here as fast as you can because seeing the northern lights has always been on my bucket list, and I hadn't seen them back then." So, I get dressed as quickly as possible, and because Durham is a very small town, it takes me like 15 minutes to run from my place to the physics department, run up to the roof where Alex and some of our other friends are waiting, and we proceeded to, wait on the roof for about 2 hours, right? Hoping to see some of these northern lights, but we didn't. And we didn't find northern lights that night, but we found friendship.
Yeah, you could say that. So, Banan, I've been meaning to ask, I've got a question for you. Why did you start the podcast in the format that you've done? Like, why did you choose these 40-minute podcasts instead of shorter content or videos?
So, I've been living alone for the past 3 years, and I've gotten used to it. The one thing that I'm still having trouble adjusting to is the silence of living alone. And to deal with that, what I've always done is have TV shows and podcasts playing in the background so the noise fills up the silence, right? And this is what I want this podcast to be like. It's like having your super nerdy, friend or sister or whatever sitting in the room with you, telling about all of the cool stuff that are happening in space. And you just have it on in the background, and it kind of feels like you have company for those nights when it's especially hard being a student living by yourself.
Yeah, I mean, that makes a lot of sense.
We've talked a couple times, and you told me that you're doing some really interesting research at Durham, and this is why you're here. You're going to tell us about the kind of galaxy research that you've been doing and stuff like that. It's very cool. Just to sort of give an intro as to what Alex is going to be talking about, I'm going to introduce what galaxies are, the different types that we have, and how are they distributed in the universe. To start off, galaxies are massive systems of stars, gas, dust, and dark matter, and other celestial objects bound together by gravity. You can think of galaxies as large cities in space, just like how the Milky Way is our galaxy, where our solar system is. It's a swirling city of stars. And there are millions upon millions of stars in each galaxy. There, you can sort of categorize galaxies into four different types: spiral galaxies, elliptical galaxies, irregular galaxies, and dwarf galaxies, and they're categorized based on their shape. So galaxies are not randomly scattered throughout the universe. Instead, they're distributed in a complex web-like structure known as the cosmic web. So they do follow a specific pattern. The distribution of galaxies reflects the influence of dark matter and dark energy, which is something that we've discussed before with Dylan. And now Alex is going to take us through why we study galaxies and how we do that.
Yeah, so just for a bit of more context, I'm a fourth year master's student in Durham right now. And so my dissertation is very much focused on galaxies. So yeah, why we study them, I guess the main reason is to better understand sort of the formation and the evolution of the universe, really. I mean, galaxies are the best tools we have. And so understanding kind of how they form and evolve basically gives us the best insight into our current understanding of physics. So how do we study them? And what do we do? So the project that I'm working on is using a large galaxy survey. So it's called DESI, which is the Dark Energy Spectroscopic Instrument. And basically this survey takes the data for as many galaxies as it possibly can. And the idea behind this is when you see all of these galaxies, you can more or less map out parts of the sky, parts of the universe. And by doing that, you can start to sort of understand the universe's structure and its composition. And these patterns tell you a lot about the underlying physics behind it. So that's exactly why DESI was created, specifically for something called the Hubble's constant, which describes how quickly the universe is expanding. And DESI did that. I'm not going to go into too much detail here, but basically by understanding how closely the galaxies are clustered together, it tells you how fast the universe has expanded. And this sort of detail, this sort of information you can get, it's incredible really, how it's possible to get all of this just with like the survey of like millions of galaxies. So that's sort of, yeah, what the background of like what a survey does and how it works.
Can you very quickly explain what is meant by the word survey?
Sure. So a survey is basically, well, think about it like, an in-person survey where you walk up to somebody, ask them a list of questions and you get all the answers. Basically just expand that a millionfold. And so this survey, or the definition of that, is sort of the data gathered for all of these galaxies in one go, if that makes sense.
It definitely makes a lot of sense. Thank you. That was a really cool way of explaining that. So what has DESI been able to do? What has it mapped? What sort of level of precision has this been at?
By doing this this DESI survey, it's the largest 3D map of our universe to date. It's a 5-year project and we're only in year 3 of it. So there's another 2 years of data being collected by this telescope. And we now know the expansion history better than 1% precision. So it's the best picture yet of how the universe has evolved over the past 11 billion years. So yeah, so that's sort of, yeah. And well, the telescope itself, it's actually in Arizona, so it's not based in the sky. It's actually based in Arizona. And what this telescope does is it's basically 5,000 telescopes all combined into one. So every time it looks up at the sky, it takes 5,000 images of different objects in like one tiny patch of sky. And the idea is that every night it will move on to a different patch of sky, and across 3 or 5 years it will have a very complete map of the universe.
So you said that a survey is like when you walk up to someone and you ask them all of these questions about themselves to collect data, right? So a survey like DESI, and here our target, like what we're trying to test here are these galaxies. What kind of information are we getting from this survey?
So from the survey, we can get the positions of every galaxy and something called the redshift. I don't know how familiar everyone is with the redshift.
I can very quickly touch on that. So basically, redshift is a technical term that we use a lot in cosmology, but for our audience who don't have a physics background, I'm going to very quickly describe what redshift is. And you can kind of imagine it. If let's say you're standing out on the street and a car drives past you. This car drives past you in 3 different phases. The first phase is as it approaches you, as it passes directly in front of you, and as it drives away. And throughout this process, the sound that you hear from this car differs through every phase. And so the phase that it's at as it's driving away from you, that sound that it makes is called the Doppler effect. And something very similar happens with light. And when galaxies move away from us, their light stretches out the same way you would imagine a sound wave stretching out when the car moves away from you. And this shifting towards the red end of the spectrum of light, and that's why we call it redshift. If we look back at the beginning of this process, when the car is driving towards you, then you can sort of imagine like the sound wave is contracting because the car is moving towards you, and we would call this blue shift instead. And so we use redshift to tell us how far away galaxies are and how fast they're moving. And this is something that, as Alex has mentioned, DESI is able to measure.
Yeah, and one thing to add to that as well is the redshift directly relates to its age in the universe. So one thing that's sort of fascinating about cosmology, and it's kind of what makes me interested in astrophysics in general, is the fact that we have so much information just based on knowing that the universe is expanding. And knowing that it's expanding at a certain rate can tell you so much about the light that you see, just from sort of understanding these basic principles.
So before we dive into your research, can you paint a picture for me of what life is like as an astrophysics student in Durham? Tell me about the early morning breakfast at the library and the long nights of coding, and just tell me about what life is like as a student in Durham.
Sure. Well, for a 4th year at least, when you're focused on your dissertation, you end up being very independent. So half of your entire year is based just on this one dissertation, which you work with alone. And yes, you have a supervisor for it, but a lot of the times you're at the forefront of research in whatever field you're looking into. So it's very hard to copy from previous work. You have to figure things out for yourself. And me, because I'm doing a coding project, it can either take 20 minutes or a week to solve, but either way, I have to be sitting there trying to figure it out myself. So if you like that sort of lifestyle of figuring it all out for yourself and being independent, then it works very well. Well, this project works very well. Durham itself, it has a great community around it. There's, I don't know how many, a couple hundred people doing the same course as me. So there's a great community and support around Durham. There's a physics cafe that a lot of people go to, and it has the cheapest coffee on campus, a total of 45p per coffee, which is sort of unheard of nowadays. I can still spend time going to the library, for example. I spend quite a few hours in there, and I've made use of the free breakfast that they have available during the weekdays on many occasions. But the good thing is with Durham and university life in general is that I still have time for other activities. So I still have time to play chess, as I'm an avid chess player, and I can still socialize and go out and do enough sport. So it's a good balance, I would say. And yeah, the project is just one part of sort of the rest of my life in Durham.
That 45p coffee at the physics building was my favorite. And just for reference, 45p, that's 45 pence. That's like 2.3 Saudi Arabian riyals. So that's very, very cheap coffee. And it was very good. Like you take you drink a little bit of that coffee and you can get like 5 or 6 hours of, lectures and research and coding done. It was super strong. Yeah.
Okay,
so now can you please tell us about your research? Because it's very interesting. It's very detailed. So you can kind of, go as much into detail as you want. Tell us about how beautiful the universe is. Yeah, just go ahead.
Well, basically, what I'm looking at is all of these galaxies. And with the data I have for them, we can basically start to find out how the light from these galaxies changes when placed in sort of different environments. So what that kind of means is kind of how does the color of galaxies change across the universe? Are there some areas further away which have redder light or are there some which are bluer? What does that tell you about the sort of expansion or evolution of that galaxy? There are questions of how clustered some galaxies are at different points. And we can look into what type of galaxies do we find in these large clusters. And we can compare that to sort of isolated galaxies. And so there's a lot of information that we can sort of dive into. Because we have such a complete galaxy survey, we have so much data to work with. We can really compare like different parts. And so there's other ideas of trying to understand sort of the star formation history, things like the metallicity, which basically explains like what is the makeup of each galaxy. And so my project is sort of trying to understand how the light from the galaxies changes depending on different things. So how far away is it? Does that affect what the light should look like? How many kind of galaxies are there like in the neighboring region? How does that affect like the light that we see? So all of those is a very data analytic heavy. So there's a lot of coding. And the idea is I do all this work and then apply that to the theory to sort of understand, what kind of makes sense and what have we maybe missed or like misconstrained.
So how is the data categorized in DESI? Like, is it by variable parameter? Because I think you've mentioned to me before that it's different groups of data, right? So how do you kind of work through that?
Sure. That is a challenge in itself. So, the information that we get from each galaxy, so we have like the color for each galaxy. So there's 3 different sort of bands for color. We call them an R band, a G band, and a V band. And these different colors are basically like different parts of the of the light you see. So some are like red color light, some is green, some is blue. And we know how much blue light, red light, or green light we see from any galaxy. We know how bright in total the galaxy is. We know we can calculate the redshift, which we've talked about before, and we also know the position in the sky. And the amazing thing about redshift is it tells us exactly how far away the galaxy is if you do the calculation. So in a way, we have a 3D map of the galaxy and the light from each galaxy based on this data. And so, that's kind of our starting point. And then we have to do a huge amount of analysis in the background just to get it to a point where we can actually start finding something new. So because the real world does kick in, there are always going to be some corrections you have to make to the instrument or to the survey itself.
And you mentioned that this project is very programming heavy. So tell me, what programming language do you use, and how does that work with the sort of goals that you have for your project?
Sure. So I'm coding all in Python using a Jupyter notebook. And one of the interesting things is, because it's such a big project, I actually have to use a supercomputer just to be able to run the code. I think it would take many years to sort of run the code that I'm trying to do on this laptop.
Can you? I'm sorry, I'm going to interrupt you because you just said something very cool. I don't know if I knew did I know that you were using the supercomputer for? You probably mentioned it. I'm a very bad listener, but can you please talk about that? What do you mean by supercomputer? How do you have access to it? Because I think that's something that people will be really interested in hearing about.
Sure. So a supercomputer basically gives you a huge amount more sort of computing power, so you can run much more complicated codes in much shorter time. So I have remote access to something called NERSC, which is the National Energy Research Scientific Computing Center, which is based in the US. And the idea behind it is it's a massive supercomputer. And if you look at the images, there's like rows and rows of like computers and like cooling systems. It's a huge computer. And that basically allows you to run like some incredibly big pieces of code all in one go. But there are some things that you still cannot do. So I don't know if people are familiar with coding, but you can't sort of list like things one by one. You can't sort of like loop through 7 million galaxies because that will still take forever. You have to be really good at writing efficient code so that you can handle all of the data in one go and like bring it through different functions. So there's a lot of practice you have to take with making your code efficient, knowing how to code correctly and in a way that you can get good results. And because there is a lot as well, you have to sort of be familiar with how to save your code in a good way and make sure that it's all like coherent with the rest of your work. So yeah, it's been a great experience for me actually. I've learned a lot and I'm still learning as I'm going through. But yeah, I wouldn't be able to do this without knowing some Python beforehand.
So, we've talked a lot about how cool astrophysics is. We've talked a lot about how interesting it is to be able to study the universe at such close proximity and in such detail. What would you say to, younger students, people that are still in high school, to inspire them to pursue this career, whether it's in physics or astrophysics, but, just in general? What
Sure.
inspired you as well to pursue this?
Well, I guess the first thing which applies to both of us is that it's incredibly interesting. So some of the work, especially in astrophysics, is some of the most like important questions that we have, or that we don't have the answers to about our universe. And so trying to like understand this, try to understand different concepts about how the world works from a physics perspective, I've always just found interesting. So I wouldn't recommend doing physics unless you are actually interested and want to know more about this. And that doesn't just go for astrophysics, that goes for everything from quantum theory to electromagnetism to all the other fascinating parts of physics as well. So I'm interested in those as well, just astrophysics more so. And I would say what I mentioned before is that in fourth year, you are somewhat at the forefront of research. So if you do progress to a master's, you are working on things that haven't been figured out yet. So you're still trying to learn like as much as possible, and there is a slight chance that your work could end up being published, or you could end up having some sort of award for it. That's not going to happen for mine, unfortunately, because the DESI collaboration is a lot more strict on publishing papers. But yeah, you have that option. And finally, the skills you gain from a physics degree are incredibly useful for sort of any job going forward. You become incredibly analytical, you have really good coding skills, you're very numerical, you're good with numbers. All of that can be used in basically any profession. So if you don't know what you want to do after university and you're interested in physics and you're good at maths, just do it, because you'll find it interesting and you'll still have a lot of future potential.
I think for me, I always get the question of, oh, you study physics, you must be really smart. Or they're like, oh, isn't it a really hard thing to study? Personally, I've always felt like I've had such a thirst for knowledge and to understand why the universe works the way it does. And that's always been a motivator for me, because yes, physics is sometimes hard to understand. You know what I mean? And you have to put in a lot of hours of, studying, going over lectures and math and integration, but
Yeah.
When you really get down to it, it's such an honor to feel like I'm sitting here and I'm learning about the universe, why particles behave the way they do, why galaxies behave the way that they do, So I would definitely recommend, studying physics for anyone who's interested in understanding the universe more, or just anyone who has a thirst for knowledge in understanding anything. Because like you said, you end up with these really cool skills that work for any industry.
Yeah, I fully agree with that.
And so in my last episode, I kind of talked about what a person can do with a physics degree. And Alex is an example of someone who wants to join the corporate world rather than go down the path of research. So Alex, please tell us about that. Why, when everyone is running away from the corporate 9-to-5 life, you're running towards it. Why is that?
Yeah, why? Yeah. Well, I guess the first thing is, at this point, I still don't know where I want to end up sort of in 10 years' time. And I know that, I'm going to be starting out as a data analyst for a consulting firm. And the idea is to gain a lot of experience and skills, and maybe one day end up in a startup or doing some work which is a lot more impactful. The challenge for me, at least with academia, is it takes a lot to do well in the field. Like you're working in a field with incredibly bright minds. I mean, just from my project alone, like I can see other people working on DESI have done incredible things. Yeah, and so you really have to be at the top of your field. You have to really know what you want to do, and you also have to be fully invested in the physics. For me, I love physics, but it's one part of my life. It's not everything. And so, for that reason, going into academia would be a challenge for me, at least, to try and succeed. So, for that reason, yeah, that's why I want to start going into sort of the corporate consulting world. Yeah, just because it suits my skill set and my kind of idea of a good life a lot better. What about you, Benan? What are your aspirations for the future?
So I feel like my goals are a bit more entrepreneurial. I hope I pronounced that correctly. And so I want to open up observatories and research facilities that focus on astrophysics and observing the universe in Saudi Arabia, because the clear weather in Saudi helps. And if I'm lucky enough, I would love to become an astronaut and go to space. And just to say that it's okay to not know what it is exactly that you want from your future. I don't think anyone needs to have anything figured out. It's okay to, just sort of take it step by step. So just to, blow people's minds before we end this episode, can you tell me how many galaxies have been observed using DESI?
So that's a great question. The answer isn't as simple as you'd expect. But in total, we've seen 36.3 million galaxies and quasars. So 36.3 million objects. And almost all of those you would never be able to see from the naked eye. So just to think about it, everything you see in the night sky right now are probably stars from one galaxy. And we're seeing about 36.3 million of them. However, it gets a little bit more complicated when actually looking at galaxies I can use, because to analyze the data well, you also want to know what the redshift of the galaxy is. And the problem with that is it's a little bit trickier to calculate. I'm not going to go into the process because it's fairly complicated and very very numerical. But out of all the redshift galaxies that we have about 7 million galaxies by the year 3 data release. So that's 7 million galaxies where we know the redshift, position, and color, and we can do all of the analysis we want with them. And hopefully by the end of the year 5 DESI project, so in 2 years' time, we should be up to 10 million usable data points. So yeah.
So we're one planet in one solar system in one massive galaxy. And now you're saying that using this telescope, we have been somewhat able to, let's take to the real numbers, observe 7 million different galaxies.
Yeah.
Take a moment.
It blows my mind. Every time I use it, it's still crazy to me. But I'm just working with that. It's all of these data points are all galaxies. Each of them have millions of stars. Each of those stars could have a habitable Earth. We do not know. And they're so far away that we might never even find them. But it's just fascinating to think about.
It is 7 million is a very big number.
Yeah, for sure.
But yeah, well, that's all the time that we have for today. Thank you, Alex, for being here.
Yeah, thank you very much for inviting me. I've had a great time.
So if you enjoyed this episode, please don't forget to subscribe and hit the little bell button so you get a notification every time I upload a new episode.